We can also take roots of complex numbers. And we're talking about integer roots here. We're not talking about any other kind of situation where I have any other kind of root that we're doing here. For each positive integer n, non-zero complex number, r times the cosine of theta plus I times the sine of theta has exactly n distinct nth roots, which are given by that following formula. Which means that if I want to take I want to take the nth root, I'm going to do the nth root of r. I'm going to take cosine of theta plus 2k pi all over n plus I times the sine of theta plus 2k pi all over n, recognizing that k is an integer starting at 0 and going to 1 less the value of n. So if I was doing a fifth root, my k values would be 0, 1, 2, 3, and 4. If I was doing like a 10th root, my k values would be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. How do we do that to solve these equations? Up to this point, we didn't really have any means of finding all the solutions to the equations. I mean, A, I could possibly do using some synthetic division means, whereas B, I really lose the ability to do that. For instance, kind of going back to my synthetic division days, if I wanted to solve the equation x cubed equals negative 1, I would go about doing it this way. So we know that negative 1 solves this equation, so that is a solution. Negative 1 to the third power is negative 1. However, there should be 3 of them. Now, if I graph this on my calculator or something, it's only going to pass through the, I'm only going to have one intersection between x cubed and negative 1. Or if I've already turned this and set it equal to 0 and plot x cubed plus 1, I'm only going to have one spot where it crosses the x-axis. The problem is, I'm supposed to have 3 solutions. The fact I'm only seeing one possibility on my graph means that only one of them is real. The other 2 are probably non-real. So, when I start solving this equation here, I'm going to use I'm going to first look at x cubed plus 1 equaling 0, which means I have x cubed plus 0x squared plus 0x plus 1 equaling 0, where x equals negative 1 is a root. So I use a synthetic division to work it out, and I end up getting that, the expression I had above, x cubed plus 1 becomes x plus 1 times x squared minus x plus 1. And so I already have the negative 1's a root. I would use the quadratic formula to find the answers for x here and get 1/2 plus or minus square root 3 over 2i. So my answers would be negative 1, 1/2 plus the square root of 3 over 2i, and 1/2 minus the square root of 3 over 2i. When I do this here, negative 1 still solves the equation. So that is an answer. However, there should be 5 answers. And if I went through the process I did before, trying to, negative 1's a root, and I'm everything like here, what I would be able to get as far as saying that x to the 5th plus 1 equals x plus 1 times x to the 4th minus x cubed plus x squared minus x plus 1 equals 0. The problem is, I would not be able to break down x to the 4th minus x cubed plus x squared minus x plus 1 anymore by anything that may show up on the calculator's graph. Because first of all, you're only going to have, I believe, one real solution for this, and that's negative 1. Meanwhile, there are 4 complex number solutions that would make this, x to the 5th plus 1 equaling 0, or in turn, x to the 5th equals negative 1. So, there are other numbers, I just have to find a way of getting them, and synthetic division and the process we had used before for polynomials isn't going to cut it here. Here's where it comes in handy to use that formula that we just came up with for the division. It's another one to do the Moivre's theorems as well. So if I use this formula here, what I'm going to do is I'm going to, again, kind of start with the fact that I have x to the 5th equaling negative 1, which I can write as negative 1 plus 0i. That's what it is in complex number form. If I take the modulus of that, I do get 1, which I can write and factor that out pretty easily because I don't change the value of anything. But when I look at -1 and 0i, I'm looking for an angle that if I take its cosine gives me -1, gives me I take its sine gives me nothing, and the pi does that. So I have 1 times the cosine of pi plus I times the sine of pi as being x to the 5th written in polar form. Now, according to this formula here, what I would do next is I would say, okay, well, to get x though, meaning taking the 5th root of x to the 5th, I'm going to do the 5th root of 1 times the quantity of the cosine of pi plus 2k pi over 5. Taking the original angle plus the 2k pi all over, the root, the square, not the square, the radical root number, plus I times the sine of pi plus 2k pi all over 5. Again, where k equals 0, 1, 2, 3, and 4. So that's what's going to give me the 5 solutions here. So now I start using this formula here, okay, and I generate the answer. So if k equals 0, then I'm going to have x equaling 1 times the cosine of pi over 5 plus I times the sine of pi over 5, which is approximately equal to 0.8090 plus 0.5879i. Pi over 5 is not one of my special angles, so here if I want to get anywhere close to being done with it, I am going to approximate the values. I can then let k equal 1. So if I look up here, pi plus 2 times pi would be 3 pi. I'd end up with a 3 pi over 5. So I'm going to have, again, the 5th root of 1, which is 1, times the cosine of 3 pi over 5, plus I times the sine of 3 pi over 5. And I evaluate those values there. I get negative 0.3090 plus 0.9511i. If k equals 2, I'm going to end up with 5 pi on top over 5, which means I'm going to have 1 times the cosine of pi plus I times the sine of pi. Again, the sine of pi is 0, so I'm going to have the cosine of pi, which is -1 times 1. That equals -1. K equals 3, again, same kind of thing. And you can also notice here is a pattern. I mean, each time I'm going down this thing, I am increasing by 2 pi over 5 along the way. So I can keep the pattern up. Another pattern you should also notice, since this original complex equation dealt with terms that had real number exponents, or more importantly rational exponents, then I should expect to have, if I have one complex number as an answer, its conjugate should also be an answer. So when I look at when k equaled 3, I end up getting negative 3.090 minus 0.9511. If k equals 4, I'm doing 1 times the cosine of 9 pi over 5 plus I times the sine of 9 pi over 5. And I get 0.8090 minus 0.5879i, which is the conjugate of what I had for the first one I did here. But those are all 5 answers. If you took each one of those, raised it to the 5th power, you would get approximately -1. I say approximately because if I took those numbers and typed them the way they are right now, I'd only have 4 decimal places. So it may be off a little bit if you do it that way. So.